Hi, everyone. Welcome to Algorithm Seminar. Today, we're happy to have Ziming here, actually at the Cambridge office to give a talk. He's the fourth-year PhD student at MIT and IFI, advised by Professor Max Tegmark. His research interests lie in the intersection of AI and physics. He publishes papers both in top physics journals and AI conferences. Please welcome our speaker.
Yeah, thank you so much for the invitation. I'm happy to be here. Can you guys hear me? Can you guys hear me well? Yeah, sure. Yeah, so I'm Ziming. I'm a fourth-year PhD student, and I'm interested in. I originally trained as a physicist, and my interest broadly in AI and physics. More recently, more broad, in AI and science. And today, I'd like to share with you guys our recent work on CAN, the Kolmogorov-Arnold Networks. So this is more or less something like math for AI. But the goal of this tool is to try to advance scientific discoveries with AI, with more interpretable AI. Specifically, here it's the CAN model. So the foundation. So the recent flourishing of AI is basically built on this universal approximation theorem. Well, mathematically speaking, it's just this formula. It's equivalent to this two-layer, multi-layer perceptrons. Of course, you can make it deeper. So it's the so-called multi-layer perceptrons. So in this talk, we are considering another alternative, another foundation of AI is the so-called Kolmogorov-Arnold representation theorem. Can we build another, AI building that is based on this CART theorem? So what is the CART theorem? It's the shorthand for Kolmogorov-Arnold representation theorem. So the CART theorem says that for a continuous multivariate continuous function f, then f can be written as finite composition of continuous functions of single variables, basically 1D functions, and binary operation of addition. So this formula looks complicated, but I will try to give you guys a pictorial, give you some illustrative picture later. It's not as as complicated as it seems to be, but the takeaway from this is that there's the only true multivariate function is the sum operation, and all other operations like multiplication can be expressed as sum and univariate functions, which I will show later. So that's the CART theorem. This looks promising at first sight, but there's bad news from 1989. Published. It's a paper by Federico and Tommaso Poggio, and Professor Tommaso Poggio is now a professor at the MIT. I also talked to him about this idea. But as early as in 1989, Professor Tommaso Poggio already argued that this CART theorem is irrelevant for neural network learning. And that seems to be really bad news for for the idea of building neural networks using this KA representation theorem. And in particular, they note in their paper that we review Kolmogorov's theorem on the representation of functions of several variables in terms of functions of one variable and show that it is irrelevant in the context of networks and learning. So this seems like really bad. Is it the end of the whole talk? Of course not. No, I'm just kidding. It's not the end. So we want to see what's really going on. Why they made such a claim that the representation theorem is irrelevant. So I again quote in their paper. They said that the theorem fails to be true if the inner functions phi qp here are required to be smooth. That means the theorem is true if you allow the inner functions to be arbitrary continuous function. But in practice, we can only model smooth functions. So that's the I see Jun. Are you raising hand?
No.
Oh, okay. Okay. Sorry. Okay. Great. So, so the question now boils down to smoothness or non-smoothness, because because the theorem does not say anything about smoothness, but we can only achieve smooth functions in practice. So that's the gap. And because of this smoothness reason, they conclude that a stable and usable exact representation of a function in terms of 2 or more layers seems hopeless. However, we are more, naively optimistic about, the usefulness of this theorem. To start off, empirically, maybe we don't care about exact representations, because sometimes approximate representations would suffice. And secondly, a common wisdom of modern deep learning is that shallow networks are not that expressive. You can basically just stack more layers. You can just go deeper. And deeper networks will have magical expressive power and will probably admit more smoother representations. And thirdly, the can-do spirit. Because you only claim that it's useless based on this math reasoning, which is reasonable. But what we care at the end of the day is whether it will succeed, empirically. So the can-do spirit just tells us, let's just make it and see how it works. So this can-do spirit leads to our CAN paper, which posted on arXiv a month ago. So yeah, so here's my overview. Welcome to interrupt me anytime if you have any questions. This is the tentative overview. First, I will introduce some math foundation. To decompose more, what's the subtlety in the theorem there, and then I'll talk about briefly talk about algorithmic implementation, followed by some discussion on the properties of CAN, including that CANs are accurate, CAN's scaling laws, and also how we make CANs more interpretable. In the end, I will include some philosophical discussion. Great. So first, math foundation. As I showed this slide one more time, basically to give you guys, show you guys another time what this, representation looks like. And the next slide, I will show you that this is actually equivalent to a neural network. If you organize them in a, you can organize these functions in this elegant way, and now, you have the input nodes, you have activation functions on edges, and you have the sum operation on nodes, and you have a second layer. Again, you have activation functions on edges, and in the end, you sum up everything, which will give you the output. So you can even, to make it more illustrative, you can even replace these symbols with 1D curves, because they are basically just 1D functions. So to characterize a 1D function, you have x and y, and that would give you those 1D activation functions. It's very it's totally transparent. You can understand what's going on inside this network just by staring at the diagram of this network. It's like the brain of the network in some sense. So what's nice about this diagram is that this is naturally just a neural network. It clearly has 2 layers. One layer, the first layer, has 2 inputs, 5 outputs, and the second layer have 5 input and 1 output. So this is basically just a stack. Just you get this network by stacking 2 so-called CAN layers. So once we have this abstraction, the CAN layer, we are now at this position to stack more CAN layers to get deeper neural networks. So this is just an algorithmic stuff. There's, we don't have very rigorous theoretical math proof why we need to do that, like how wide, how deep we need to get. We just say, hey, we are allowed to do this because we have this CAN layer, and in the spirit of modern deep learning, just make neural networks deeper. We can stack more layers to make the CANs deeper. But maybe a little bit discussion why we want to make CANs deeper. So we need to revisit what's the main claim in the 1989 paper, why they say that the Cart theorem is irrelevant for machine learning. The main argument was that for the original two-layer constructions, the inner functions can be very pathological. It can be very non-smooth. So in practice, they may not be learnable, because to make things learnable, we use gradient descent, and to make the gradient descent feasible, we need the landscape to be differentiable, and the functions also to be differentiable. So here's one quick example. We have this formula involving exponential, sine, and the squared function, and it actually needs 3 layers. It needs 3 layers to do the task, because there are 3 layers of compositions. And on the right, I show how a 3-layer can, in training, can have this expected symbolic functions emerges. Although this symbolic functions, they appear symbolic, they're actually parametrized as spline functions. I will dive into the details later, but for now you get the sense that these 1D functions are learnable, and we also encourage the network to be sparse. So in the end, we not only do the task well, but also gain some insight, gain some interpretability from the training. All right, so once we understand what are CANs, we are now can compare MLPs and CANs side by side. So MLPs are inspired from universal approximation theorem, while CANs are inspired from Kolmogorov-Arnold representation theorem. So they basically come from two different math theorems that guarantee the universal approximation property of these representations. So intuitively, we can also plot MLPs and CANs side by side, and you see that MLPs have learnable linear weight matrices on edges and fixed activation functions on nodes. But by contrast, CANs, they have learnable activation functions on edges, while they have some operation on nodes, which does not involve any learnable parameters. So basically, MLP is an interleaving of linear matrices and nonlinear transformations, while CAN is basically a stack of CAN layers, and the CAN layers can do both things, can not only combine these variables, but can also apply 1D nonlinear activations. So it's like the linear matrix and the nonlinear transformation all compactified inside one CAN layer. So in both cases, we can make this networks deeper. All right. So some brief algorithmic details in case you wonder. Actually, they're not that interesting, so I will quickly cover that. The way we parameter, so I said that we have learnable 1D activations on edges. How do we make these functions learnable? So basically, we parameterize these 1D functions as splines, and by splines, and for B splines, we have this local B spline basis. And the function is basically just a linear combination of this B spline basis and this coefficient Ci. They are the only learnable parameters. And what's nice about this spline parameterization is that it's easy to switch between a fine grained to a coarse grained and vice versa. So you have this flexibility inherited from spline. Well, this is even more detailed and subtle, but because when I developed this CAN model, I kind of got stuck And finally, these are the solutions to make CANs trainable. So I still want to share these little tricks. The first trick is the so-called residual activation function. It's a bit like residual connection, where we have like an identity operator linking between the input and output of a block just to make the gradients propagate better. And secondly, like in how we have used Xavier or Chimie initialization, the initialization scales also matter a lot for CAN initialization. And finally, because we use splines to parameterize this 1D functions, and for splines, usually we have a bounded region of inputs. So we need to address this question, because in neural network training, the inputs of later layers can be trainable, can evolving in training. So we want to update the spline grids on the fly to accommodate that, to make sure that the grids will always support all the incoming activations. Yeah, so one good property of CANs is that it can be made very accurate, and this is inherited from the splines. And we can also see there are some nice scaling laws of CANs. So I mean, people have talked about neural scaling laws a lot, but scaling laws is not a very new idea. It's a classic old idea. It's a classic old concept, even in mathematical, in numerical analysis, where your approximation error L is a power law of the number of parameters, the number of model parameters or the number of splines, whatever, and to the power of minus alpha. And here we call the alpha the scaling exponent. And we want alpha to be as large as possible, because that would promise that when you scale up your model, your performance will get better. So if we just consider a function with d input variables, in general, it will have curse of dimensionality when d is very high. Here, curse of dimensionality is in the sense that if we want to use k order k polynomial splines to approximate this function on this d-dimensional uniform hypercubes, then the scaling exponent is k plus 1 divided by d. So here, the divided by d is an indicator for the curse of dimensionality, because when d is in practice, d can be very large, meaning that the scaling exponent can be really small, which means that when you scale up your model, the improvement in performance you can squeeze out can be really small. But on the other, but by contrast, if a function can be represented as a CAN, then it's a great news, because the idea of CANs is saying that to approximate like a high dimensional function can be decomposed into 1D functions. So to learn the high dimensional functions, the only job you need to do is to learn these 1D functions. And the learning and these 1D functions are easy to learn in the sense that d now equals to 1. So you can have a scaling law with the exponent k plus 1, which is much better than k plus 1 divided by d, which sort of beats the curse of dimensionality. But one caveat here is that we need to assume that here for the target function there exists a smooth Kolmogorov-Arnold representation, but that's something we are very unclear about. If you ask me, do we expect languages to have such card theorem, I would say I don't know. But according to current scaling laws, we would estimate d to be around the order of 10 or 20. But I see there are hopes that we can reduce the dimensionality further down, even if we cannot reduce it down to all the way to 1. So here's some examples to show that the previous theory is correct, at least for some symbolic formulas, as we show here. So here we demonstrated five examples, and for each case, the scale the CAN model is represented by this thick blue line, And these lines, and the dashed red lines are the theoretical limit, that is n to the -4, because we use cubic splines, where k is 3. So we have a -4 theoretical prediction. And then we compare our empirical scaling laws to the theoretical scaling laws, seeing that they're quite aligned. Although for the second to last cases, it's 100 dimension, so the task is a bit challenging, and there could be some optimization issue. But still, CANs are performed much better than MLPs, where MLPs suffer a lot from the curse of dimensionality. Yeah, another point I want to make with the last plot is that sometimes we're not sure how deep we want to make CANs to be. In this case, we need a 3-layer CAN to do this task. But if we just, being naive and use the original 2-layer CAN, you will see that the 2-layer can perform quite bad as MLPs. So this sort of brings in some subtlety when we try to determine the architecture. Sometimes we don't know how deep we want to be, but what we know for sure is that deeper CANs will have more expressive power and will more likely to give you smoother representations. So you might be also wondering, so in the last slide, we just tried the symbolic formulas, which sounds quite contrived. Although because I'm coming from a physics background, symbolic formulas seem quite natural to me. But from people in machine learning, they may feel that, oh, this is quite contrived. So we want to take a step further and see that how far we can go. But I still use something that I'm familiar with, which is the special functions. They're less contrived than symbolic functions in the sense that they do not admit closed form analytical formulas, but they still used a lot in mathematical physics. So here we sort of know that these special functions do not have exact Kolmogorov-Arnold representation, but we still are trying to train CANs to fit these tasks, and we find that it does not always have the -4 scaling as the theory predicts, which sort of agrees with our expectation, because we sort of expected that these functions do not have exact Kolmogorov-Arnold representations, but nevertheless, the blue lines represent for CANs are much better than the orange lines for MLPs. The way to read these figures, so the x-axis is the number of parameters of the model, y-axis is the loss, is the RMSE, basically the loss function, the square root of MSE. And for either CANs or MLPs, we train thousands of models and place these models, put these models in these 2D planes, and we only show the Pareto frontier. So here we want the Pareto frontier to be bottom left. The more bottom, the more left, the better. So you can see that the blue Pareto frontier are to the bottom left of the orange lines, which represent the MLPs. So besides function fitting, we can also solve partial differential equation using the physics-informed learning paradigm. So basically, we want to we have a partial differential equation with certain boundary condition, and we use CANs to represent the target solution. And again, if you see the training curves, you see that MLPs usually first go down quickly and then easily plateaus, or at least decreases slowing down. But for CANs, we can leverage this grid extension trick, basically going from a coarse grid to a fine grid, to a fine-grained grid. And you see that once the time we do that, you see a sudden loss drop. Which is good in the sense that you can make your model as accurately, as precise as possible, given that you have sufficient data. Well, one thing we can one thing cans can do for sure, but MLPs cannot do, is that after training the PDE, we can plot the solution as this, can diagram. And if you look closely, you may observe that for the first layers, the activation functions are all linear, and the second layers, they look like science. So we can basically apply a symbolic regression to these activation functions and obtain the whole formula. And after that, we can further train, the formula with some tunable parameters, and in the end, we can achieve the machine precision loss, which is impossible otherwise if you just have if you just train a black box neural network. So here you not only get extreme precision, you can also get some interpretability out of it. Another thing, well, here's another quite contrived example, but I still but I find the property to be quite interesting, so I still want to share this with you. So usually, so in some cases we care about continual learning, where data are not provided to you, in one shot, but provide you in a streaming way. So let's suppose we want to feed this one big function with 5 peaks, and the data are coming in 5 stages, and each phase will present you only 1 peak. And for cans, when you observe, when cans are receiving more data, they do not forget about old data. But this is not true for MLPs, because for MLPs, you see when MLPs try to feed the new data, it just naturally forget. It just unavoidably to forget about the old data. Besides accuracy, as I mentioned, the initial motivation for me to make cans is to make cans a better tool for scientific discovery. And here I will give you a few examples how we use cans to aid human scientists to make scientific discoveries. So the first case, so for this toy example, is this supervised learning task where you have input variables x1, x2 to xn, and you have one output variable y, and we want to figure out the relation between. We want to find a mapping that can map these input variables to the output variable. So here I show some. Cases. It looks the plot looks a bit busy. I apologize for that, but maybe you can focus on the first two, the multiplication and the division. So how does a can do multiplication? The multiplication task is that you take in x and y, and you want to output. You want to predict x multiplies y. It's interesting that I did not expect cans would implement multiplication in this way, but after I trained my cans, I realized that it discovers a really clever trick here. So basically, there are 2 hidden nodes here. One hidden node is computing x plus y followed by a squared activation, so you get x plus y squared. And the second activation, the second hidden node has activation x squared plus y squared, and you have followed by a minus sign. So basically, the way you get x, y is by using this weird, maybe not weird, equality, x y squared, x plus y, the whole thing squared minus x squared plus y squared equals to 2xy. So that's how it computes the multiplication. The second example is the division example. Here, I confine x and y, both x and y, to be positive numbers. So after training, there is only one active hidden neuron, which stands for log of x minus log of y, followed by an exponential. So basically, from math, we know that division is equal to subtraction in the exponential in the log scale. So it rediscovers this trick, which is quite neat. Yeah. So I wrote this in the paper, which receives a lot of criticism, but I'm still quite proud of it. I think that there is an relation between CANs and language models. I think the reason why language models are so transformative is because anyone who can speak natural languages, language models are accessible to anyone who can speak natural languages. But when we care about science, the language of science is not natural language. It's more about math, it's more about mathematical formulas, or more concretely functions. And because CANs are composed of 1D functions which are interpretable, so when a human user stares at a CAN, it's like communicating with it using the language of functions. So I will give you one more example to give you a sense of what I mean by communicate with CANs. So here is again a task, a very simple symbolic task, where a symbolic formula. So we have x and y as input, and we have this symbolic formula as output. And in step one, we train the network to encourage the network to be sparse, and then we can in step two we can prune the network to get the most important to get the backbone, which really do the computation. And then we noticed that the bottom left activation looks like a wave, so we should probably set it to be sine. And the bottom right looks like a quadratic, looks like a parabola. We probably need to set it to be the squared function. And also the activation in the top looks like exponential. We probably need to set it to exponential. And after doing that, we can further train the network down to machine precision, and finally output the symbolic formula. And until this point, we totally understand what this data set is about, what the task is about. So we can gain some extent of interpretability by interacting with CANs. So here's one. So more pictorially, as I said, CANs are like aliens, but luckily we can communicate with them. This is like how in the Netflix series Santi, the Trisolarians, how they communicate with each other is that their brains are totally transparent. So they have no secret to hide. You can basically understand everything by just read their minds. So let's consider a scenario where my advisor, Max, is communicating with CANs. So we could suppose that the conversation could go like this. So Max says, here's my data set. It contains the mystery of the universe, but I am unable to figure it out. Could you please figure it out for me? And CAN say, yes, I'm ready. Here's my brain. So CAN will initialize itself to be this structure. And then Max asks CAN to train the brain. And after training, you see that it got this sparse structure, which looks promising, but still there are some unnecessary redundant connections. So Max asks again, it looks like there's some redundancies. Can you prune it? So yeah, I can say I can prune it. And after prune, we got this tiny subnetwork. And Max go all the way to the symbolification. Can you further symbolify it? Yes, I can. So in the end, we got this symbolic formula, which is totally transparent, and at least scientists would find it interesting. And I mean, nowadays machine learning are behaving like black boxes, and it's our wildest dream to fully understand what's happening inside these black boxes. Well, in comparison, so previously it's like a communication with CANs. Let's suppose there's a communication with MLPs. What will happen? So with MLPs, Max went to MLP, says, here's my data set. It contains the mystery of our universe. And MLP says, yes, I'm ready. Here's my brain. It looks like something like this. And Max asks, train your brain. And MLP said, done. Now Max got a bit confused because it looks like exactly the same at initialization. There's still many messy connections. It looks as messy as the initialization. So can we get anything interesting or meaningful from it? And MLPs are actually, so the MLP is like, I actually trained it. The loss is pretty low and it can make reasonable predictions, but it's just that the connections are too complicated. And yeah, and now Max got confused. What's going on? I cannot understand what's going on. And now MLPs act like you stupid humans. We're just doing some, alien kind of math, which is uninterpretable to you human beings, but we still can do the task as well as you do, or even better than you humans can achieve. Right. So this is just one, imaginary scenario where we have the potential conversation we could have with our models. And here and in the following, I want to show you two concrete examples in scientific research that we will encounter, and how we use scans to facilitate scientific, our scientific research, and in the end, help us speed up scientific discoveries. So the first example is the knot theory example. It's a paper published by Google DeepMind 3 years ago, called Advancing Mathematics by Guiding Human Intuition with AI. They showed that AI scientists can collaborate together to discover a new relation in the knot dataset. So, well, the knot theory aside is knot theory I don't fully understand, but the question is formulated as such. So each knot has 18 topological invariants, which are basically numbers, and we want to figure out the relations between this invariants, these variables. So what DeepMind did was that they disentangle, they select out one variable called the signature, treat it as the output, and then put all other 17 variables as the input. And they treat the problem as a supervised learning, taking in the 17 variables and want to predict the 18th, the signature variable. So that's how they set up the problem. They trained the MLP, and they used attribution methods to identify which are the important input variables. That's something done by AI, but then the human scientists come in and come up with the slope concept. They define a symbolic formula based on this AI discovered important variables, and then the human scientist proved the formulas. So we asked the question. This actually sounds a lot of painstaking. Actually, the role of AI is quite minor in this project. Can we automate as much as possible? And can we even discover something beyond this paper's results? So the answer is yes, we can. So firstly, we can rediscover the relevant variables with much less pain. Basically, we used a can with just one hidden layer, two can layers, with only one hidden neurons. Surprisingly, it can achieve comparative accuracy to DeepMind's giant MLP. Basically, the MLPs they use have each layer has 300 neurons and has 5 layers. But here we only have one hidden layer and one hidden neuron, and it can do the task equally well. So this gives us a sense that for some scientific problems, it's not that scale matter. What matters is interpretability. You can even achieve very good performance with a very tiny model. But the point here is that what kind of insight can you gain from it? So from this plot, we can clearly see some connections are strong, some connections are weak, and this is indicative of which variables are important and which variables are less relevant. So here's just some comparison of the parameter count, and we are able to reduce it from around 1 million parameters down to 100 parameters, and we can further turn the CAN model into symbolic formulas, and we can achieve the trade-off between accuracy and complexity. We can not only obtain one symbolic formula, but we can obtain like a Pareto frontier, a family of symbolic formulas trading off between accuracy and complexity. And yeah, this slide is really fun. I'm really proud of this result. It's something that Google DeepMind did not discover, did not explore, but we are able to go to this unsupervised learning setup. Basically, we treat all the 18 variables on the equal footing, and we try to discover the inner relations in an unsupervised way. And we find that there are three main relations here. The first relation is basically rediscovering the signature relation, because we see that there's a strong connection. Maybe you cannot see here, but the last variable is the signature variable. It has a strong connection coming out of it. And for the other two, relations, I myself was quite surprised by discovering these relations, because I wasn't expecting such thing to happen. But maybe because I do not have a strong background in knot theory. But then I present these results to my collaborators who are experts in knot theory. They told me that, actually the second relation is by definition correct. Actually, the first variable is by definition the multiplication of the second and third variable. So that's why there's a relation. So that's a bit disappointing, because that's something we already know in the literature. But that's again reassured that we're discovering something meaningful, not discovering some spurious relations. And for the third relation, actually, it took my collaborators a few weeks to realize that, this is something known in the literature. We're not discovering anything new, but again, it's reassuring that we are discovering something meaningful that is known in the literature. But we need to highlight that here we only use a can with just one layer to learn the variable. Hypothetically, we can make networks deeper to obtain more complicated formulas, and in that case, hopefully, we can really discover something not known yet and make new contributions to mathematics. Another example we used, tried is for physics application. I probably won't have time to go into the details of the problem setup, but the basic takeaway is that we are able to figure out the symbolic formulas of boundaries of phase transitions. And what are phase transitions? Basically, water have many phases. It can be water, it can be ice, it can be gas in different physical parameters, and we want to figure out when the phase transitions happens, and even we want to figure out the symbolic formulas for that. So I won't go into the details of it, but one thing I do want to highlight is that cans can have both automatic mode and manual mode. If you feel lazy, you can just click the button that I want to do the fully automation to review the symbolic formulas. Yes, can do that for you. But if you want to be more fun and you want to communicate with your CAN model, you can then use the manual mode by manually setting some activation functions to be something that you would guess. So this makes it like a collaborator, which you can interact with it. You can interact with the model. Not only that, the model is acting just like an oracle that can act like an AI god that tells you everything. No, it's more like a collaborator, which you can truly interact and collaborate with. In the end, you and the model will agree, will converge to some common ground, and finally make a conclusion together. Yeah, and a few philosophical discussion about cans. There are people asking me what a can's good at or bad at. So I have to be honest that the boundary is still unclear to me. It's something to be explored. But let's do a thought experiment. Let's think of a teacher-student setup. If the task generated by teacher, if the task is generated by a teacher can, then a student can will be more likely to perform better than a student MLP. If the task is generated by a teacher MLP, then a student MLP will be more likely to perform better than a student cans. So the real question is, for the tasks that we care about. For me, I care about our physical universe. I care about science. For me, test science. If science is generated by some sort of networks, is science generated by cans, or is science generated by MLPs? So this is all about inductive biases. A network performs well on a task if the inductive bias of the network agrees with the inductive bias of the task. So at least in our paper, we showed that cans are good at science because cans have better inductive biases with science. So at least we know that cans will be a promising tool, at least in science. But it's to be honest, it's very unclear how big a role can will play in machine learning in general. And just to give more philosophical thinking of what's the difference between CAN and MLP. For me, my feeling for cans is like cans are like clock. Can is like clockwork, where pieces are customized, have clear purposes, and each piece can have very complicated shape. But it's easy to tear them apart and reassemble. Like the way they combine is very simple for cans. But MLP is more like a house of bricks. Pieces, that is the bricks, are produced in the same way, are produced in a very simple standard way. But it's difficult to tear them apart. Once you build the building, it's hard to tear the bricks apart and then reassemble them. So MLPs are more like so MLPs are more aligned with the philosophy called holism. That is, each individual part are not interpretable, are not that important. What matters is the connection between these individual parts. These individual parts are complex. However, cans are more aligned with the reductionism. That is, we believe that we can decompose, we can tear apart complicated stuff into individual parts. And the way we tear them apart can be very simple, although the individual parts can still be complicated. So so from the philosophical level, both cans and MLPs are expressive, but their complexity actually have different origins, have different sources. Cans, the source of complexity in cans come from the complexity of each individual parts. That is, the learnable 1D functions can be very complicated. However, the way to combine these 1D functions can be very simple. It can be as simple as a compositional sparse graph, something like that. But for the source of complexity for MLPs coming from the complex interaction or connections between different neurons, although each individual neurons can be quite simple and standard. Even more wild question: are cans natural? Because we're talking about artificial neural networks, but are there natural counterparts in nature? So the first question is: are cans physical? And the short answer is, unfortunately, cans are not that physical. What we call physical might be this, Feynman diagram where we have particles, they're flowing freely in free space, and then they collide, and on the nodes they have some complicated interactions, and then they split out into new particles. So in that sense, interesting things happens on nodes rather than on edges. But in cans, interesting happens on edges. In MLPs, interesting things happens on nodes. So in this sense, cans, the Feynman diagram is more like MLPs, less like cans. And people also ask, are cans biological? Because MLPs are sort of inspired by the neurons in our brains. Are there any biological counterparts of cans? And the answer is yes. And actually, in our retina, the way we perceive the nightness is actually more like cans, in the sense that each cell receives the light, and each cell apply a nonlinear transformation first before applying this sum operation. So in this sense, it's more like cans. Well, So it has been a month, and there have been created a lot of enthusiasm around the topic of cans, and people have applied cans to various domains, including graph, reinforcement learning, partial differential equation, diffusion models, and have translated cans in different languages, and also because people try to make cans usable in machine learning, a lot of improvement in efficiency have been done, and also people have even tried to replace MLPs with cans in transformers to see how to see the potential of cans for language models. Yeah, so that's everything I would like to share, and I'm happy to take questions if you have any questions.
Thanks for the great talk. So I have a quick question. Maybe I missed this. How did you enforce the network to be sparse?
Oh, yeah. Great question. I did not mention it. It's like something like L1 or L2 penalty. But here L1 are defined on the function space. Basically, we defined an L1 norm for function, and we in training we have that penalty.
I see that in the network there are some of the connections are faded out. So if I understand correctly, the connections are simple summations. How come some of them are like disconnected? How did you decide on that?
Maybe I can go back to maybe this.
Yes.
Yeah, like in the top middle figure, only the there's some disconnected components. I guess this is due to insufficient training. If you train longer enough, they will vanish. But either way, you can use pruning to make them go away.
But isn't the connections all simple summations instead of you don't train the weights, right?
Oh yeah, so on the nodes it's simple summation. So there's nothing trainable on the nodes. Only the 1D activations on the edges, they're trainable.
I see. So if the 1D activation is small enough, you just prune out the edge. Is that right? Or
so there is no linear weight at all in cans. So each weight in MLP is replaced by a 1D function.
And the pruned out edges are just those where the activations are all zero.
Yes. Yeah.
I see.
Exactly. Yes.
Okay. Thanks.
Yeah.
If there are no other questions, let's thank the speaker. Thanks.
Yeah. Thank you.